Okay, we have been discussing simultaneous vibration and rotation. Vibrational rotation plus rotational energy levels. The expressions are going to be valid for diatomic, two-atom molecules. We label them and this is vibrational energy plus rotational energy, and if we write explicit expressions, this is F0 times V plus 1/2 plus E times J plus 1. This is rotation energy, this is vibration energy. Here there are two quantum numbers. One is V, the other is J. These are independent quantum numbers. Vibration quantum number V takes values 0, 1, 2, and so on. Same is true for the rotational quantum number. And in general, the vibrational energy parameter here is much larger than the rotational constant. We had given an example for hydrogen chloride molecule. This quantity was 3000 wave number, whereas B was only 10 wave number. That's what we mean. This number is much larger. All right. Let us now show display these values using an energy level diagram. This is I will first indicate values on this axis, the numbers which correspond to the vibrational part. So for V equals 0, we have 1/2 times F0. So if this is 0 here, now this is 0.5 F0, just this part. Next vibrational energy level is when you put V equals 1, which means 1.5 F0. The one after that is when you put V equals 2 to this expression. This is 2.5 F0. We may continue like this for other higher energy vibrational states. So let us put ... Now, I will draw a line. This is for V equals 0. And another line here for V equals 1. A third line for V equals 2, and so on. Okay. Now what I do is, I come to this contribution here. For each one, either this one or that one or that one, there is an addition from the rotational energy. Now, I'm looking at this part, this vibrational level, the ground vibrational level. For J equals 0, there is no contribution. so that this also corresponds to J equals 0. For J equals 1, we have 2 times B plus this value. So on the axis, this is, I mean this value 0.5 F0 plus 2B. So here we have a rotational level. This is for J equals 1. Now, the next value is when we put J equals 2 here, then 2 times 3 is 6. 6B, so I will indicate it as plus 6B. This is for J equals 2. Let us indicate one more. For J equals 3, 3 times 4 is 12B. So suppose it is here. Notice the difference between this vibration level and that vibration level is F0. F0 is, say, as a concrete example, HCl molecule. It was 3000. Note here, B is, on the other hand, only 10 wave number. 10 times 12, 120. Whereas the actual spacing between one vibration level and the next one is 3000. So there are many more rotation levels can fit between this level and that level. These dots indicate that. Okay? All right. Let us fill this one. Now, for the next vibration level, V equals 1, J equals 0, it is this. Now, we continue adding contributions from the rotation level to this vibrational level. Here, V is 1. The vibration energy is 1.5 F0 plus the rotational contribution, which comes from here. So, it is similar to what we have shown for the ground vibration level. Here we have plus 2B. This is for J equals 1. This plus 2B means 1.5 F0 plus 2B. According to this expression. For V equals 1, J equals 1. The next value, similar to this one, plus 6B. J equals 2. The next one, plus 12B. This is J equals 3. And then it goes on. As in the ground vibrational state, there are very many rotational levels which fit between this lowest vibration level and the next one. Same thing is true for this vibration level and that one. So this is a graphical way of showing this expression, the numbers which are generated from this expression. Now, let us consider light absorption by a sample of gas molecules and see what happens. Now, as a result of absorption, light photon absorption, molecules in some given initial state will make a transition to higher energy states. For example, molecules in the V equals 0, J equals 0 level can make a transition to that level or to some other a higher energy level. But here we have to remember the rotational selection rule. What was it? In a transition, delta J must be either 1 or -1. In absorption from the molecules at the lowest level, the lowest level has J equals 0. Therefore, the only possibility is make a transition to J equals 1. There can be no transitions to J equals 2 or J equals 3 level because of this selection rule. Molecules, remember that we have to think about the initial states of the molecules in the sample. The sample, gas sample, there are millions or trillions of molecules inside the gas sample. Now, at some temperature T, say room temperature, 300 Kelvin, at the given temperature, we need to have an idea about the vibrational states of these molecules. The answer to this question was found by applying Boltzmann distribution to the vibrational energy levels, and we had done that in the last lecture, and our conclusion was that at room temperature all the molecules are in the ground vibration level, which means the vibrational states of all of these molecules in the sample is just V equals 0. There are no molecules initially at V equals 1 or V equals 2, etc. Is that clear? So we can safely assume that all the molecules in our sample are vibrationally in the ground level, V equals 0 level. But we also need to think about what about the rotational distribution? The rotational distribution of the molecules is also obtained by using Boltzmann distribution, but this time using rotational energies. And we had done that before when we discussed only the rotational energies and rotational transitions. They correspond to this level, this part. This is the initial distribution of the molecules. In other words, all the molecules are vibrationally in the ground level, but rotationally there is a distribution. Some of the molecules are in the lowest level, some others are in the J equals 1 level, still others are in the J equals 2 level, and so on. And the relative populations of these molecules over the various rotational levels are obtained by the Boltzmann distribution expression, and we had done that before. If you remember, for HCl molecule, HCl molecules in the sample at T equals 300 Kelvin, population of J equals 3 level was the highest. Remember? Now we can discuss the possibilities for light absorption. If the now imagine you start with a low frequency of light source and then gradually increase the frequency. Then the first transition will occur, which will cause the molecules in the J equals 0 level to make a transition to J equals 1 level. Now, there are, of course, molecules already in J equals 1 level. Those molecules could make a transition to that level. Molecules in the J equals 1 level will make a transition to J equals 2 level according to this restriction, the selection rule, for rotation selection rule. Now there are molecules in J equals 2 level also, some molecules. Those molecules, when they absorb photons, they will make this transition. Okay. The photon frequencies that you see here, what are they? The difference between final state minus initial state. Say 12B minus 6B is 6B. 6B for HCl is just 6 times 10, 60 wave number unit, centimeter minus 1 unit. Those photon energies are much smaller than the difference between vibration levels. The difference between this level and that level is just F0, but F0 is 3000 wave number. Which means all of these transitions that I show here are such that the vibrational states are the same. Vibrational state of the initial and final state are the same. You see, the vibration state of this level is also J equals 0. This one also V equals 0. This one also V equals 0. So, well, vibrational state is not changing here. What's happening? The rotational state is changing. Only the rotational state is changing. This part of the frequencies of light which are absorbed correspond to the pure rotational transitions because the vibration state is not changing. The ones that I show here correspond to pure rotational transitions. In this part, only the delta J equals 1 plus 1 selection rule is operative here. Intensities of these transitions are proportional to the populations of the initial states. For example, intensity of this transition is proportional to, because initial state is this state, proportional to the population of this level, which means it's proportional to the number of molecules at this energy level. Similarly, intensity of this transition from J equals 1 to J equals 2 level is proportional to the population of the molecules at the J equals 1 level, because J equals 1 level is the initial level in this transition. So we have done the calculation for this part in our rotational transitions, which was at the beginning of this lecture. Right after we have introduced the Boltzmann distribution. And now we consider higher energy light frequencies such that vibration state will change. Now, when the vibration state changes, if any one of these levels, if it goes to this part, for example, then because in this part V equals 1, which is different from V equals 0, the final state has a different vibrational level. Of course, we have to think about possibilities, like do we expect transitions from one level initially here to that level, some level above the V equals 2 level. This time, what's happening? Direct transition from V equals 0 to V equals 2 level. The question is this expected? And here, there is the vibrational selection rule we have to apply. The vibrational selection rule is delta V, the change in the V quantum number, vibrational quantum number, must be +1 for absorption. There is also -1. The second one corresponds to emission for vibrational transitions, but we are talking about absorption here, so it is the +1, which means it is possible the transitions from the levels which belong to V equals 0, which are these levels, it is possible to make a transition to one of these levels such that delta J equals +1 or -1. We are going to examine that. But transitions from any one of these levels to higher than, this V equals 2 or any higher vibration level are forbidden. No transitions will take place to the higher vibration levels because of this condition here, this vibrational selection rule. The vibrational quantum number changes just by 1 unit in an optical transition. Now, graphically, remember, initially, the molecules, all the molecules are in the vibrational ground level. All of them have V equals 0 initially. And there is a distribution over rotation energy levels, which belong to the ground level. So, let us consider molecules which are in the V equals 0, J equals 0 level. All right? And then we are considering large energy photons, which will cause transition to such that the V vibration level is going to change. So, from here to now, the question, is this expected, is this transition? We see that V equals 0 to V equals 1, therefore delta V is +1, that's okay, this condition. But simultaneously, we have to think about rotation selection rule. In this transition that I show you here, initial J is 0, but what is final J? It is also 0. Therefore, J did not change. According to this rule, is that allowed? No. Therefore, this transition is not allowed. No such photon. However, is this transition allowed? It is allowed because both conditions are satisfied. Of course, for all of these levels, delta V is satisfied. But we have to make sure that J equals delta J rule is also satisfied. Initial J is 0, final J is 1, delta J is +1. Therefore, is this transition allowed? Yes. What is the energy of the photon which causes this. It is 1.5 F0 plus 2B minus the initial energy, which is just 0.5 F0. That means the net result is F0 plus 2B is the energy of this photon, which will cause the absorption. Okay, now the molecules in the lowest level, V equals 0, J equals 0 level, can they make any other transition in the higher vibrational level, say to this level or to that level? If they, from here to here, is that allowed? What is J? In that case, J is 2. Initial J is 0. Delta J will be 2. But the selection rule says delta J must be only 1. So the molecules with V equals 0, J equals 0 cannot make any other transition in the upper vibrational level. The only possibility is to J equals 1 level. What about molecules in the J? Remember, there are molecules in J equals 1 of the ground vibration level, also J equals 2, also J equals 3. There is a distribution there. All right? So consider those molecules which are initially in J equals 1 level of the ground vibration level. Is this transition possible? Allowed? Initial J is 1, final J is 2. 2 minus 1, 1. Delta J is satisfied. Okay? But is this transition allowed? This is absorption. But again, vibrational state changed. So delta V is plus 1, which is satisfied. What about J? Initial J is 1. Final J is 0. What is delta J? Minus 1. This is absorption. Remember, it is not emission. As you see here, absorption. You need external energy to cause this transition. But for the rotationally excited levels of the ground vibrational level, it is possible for such molecules to make either a transition to such that delta J is minus 1 or delta J is plus 1. Both are possible. So this is a graphical way of showing the transitions, but in general, we can split or divide the transitions into the upper vibration levels into two types. In one type, J to J plus 1 transitions. The other type is J to J minus 1 transitions. J is the initial J in the ground vibration level. The symbol J refers to initial J, one of these. I will consider separately J to J plus 1 transitions, then J to J minus 1 transitions, then combine them. We have initial energies V equals 0 for all of these. Initial energies are 0.5 F0 plus B times J plus 1 where J is 0, 1, 2, etc. Final energies are these energies. The vibration part is 1.5 F0 plus I will put, because I'm talking about J to J plus 1 transitions, the final J will be J one more than the initial J. So I will write this J plus 1 times J plus 2. Here I have replaced J with J plus 1. Then delta E, the energy difference between the final state and the initial state. This expression minus that expression is F0 plus 2 times B times J plus 1. Here for J equals 0, 1, 2. Remember, J is the initial initial J value. So, if we write here frequency of light increasing to the right, we are going to indicate which frequency of light or frequencies of light that have been absorbed in such transitions. Transitions in which initial J increases by 1 unit, J to J plus 1 unit. All right. Because this expression is equal to h times frequency of the light. Delta E equals, all right. Now, if this is on the scale F0, according to this expression, the smallest delta E will be with J equals 0, so the smallest value for delta E is F0 plus 2B. So here I will write plus 2B. This is one of the photons that could be absorbed by the molecules in this sample. Numerical value is F0 plus 2B. Okay? There is no absorption at this point because this corresponds to J equals 0 to J equals 0 transition, which is forbidden. Delta J must change, either plus 1 or minus 1 in this transition. The next photon, the next energy, higher energy photon is when you put J equals 1 to this expression, then you get 2 here, 2 times 2 is 4B, F0 plus 4B. That one I indicate by this mark. The next one, put J equals 2. 2 plus 1 is 3 times 2 is 6. F0 plus 6B. Now let us indicate for this transition, what was the initial J? Which value for J I have put in that expression to get F0 plus 2B? J, That is the initial J. 0. What is the final J for this transition? Delta J is plus 1, isn't it? 0 to 1 transition for J. What about this one? What was the initial J? 1. The final J is 2. This one, initial J is 2, final J is 3. We can continue like this, obtaining all the possible photon frequencies or photon energies which are possible in this sample. This expression gives that. Now, you see that the energies of photon in J to J plus 1 transitions are larger than F0, which is the vibrational spacing. This part of the absorption is called R branch. You see, the photon frequencies are classified in two types. One type have frequencies larger than F0, the other type have frequencies smaller than F0 on this side. And PR, alphabetically, PR, but please note that the direction, increasing direction is frequency. Sometimes such diagrams are drawn using wavelength. In that case, it is reversed. So if it is in terms of frequency increasing to the right, then in the same direction, alphabetically, P first, then R. All of these, or given by this expression, correspond to R branch. There is also P branch. P branch correspond to J to J minus 1 transitions. In other words, this one is one of the photon frequencies that belong to P branch, while J equals 1 to J equals 0 transition. In other words, delta J is minus 1, isn't it? So, we write this expression, initial energy. Now, for the final energy, we put J minus 1. Replace J with J minus 1. I will simply write the final expression. In this case, delta E is F0 minus 2B times J. Of course, here, in J to J minus 1 transitions, because J is still the initial J, J quantum number of the initial state, this J must start with 1. In other words, there is no J to J minus 1 transition from J equals 0 level. The first transition is from J equals 1 level. Because in the upper state, there is no J equals minus 1. J always starts with 0, 0, 1, 2, 3, etc. So therefore, note that the starting value for J equals 1. Whereas in this expression, J starts with 0. Now, using this expression, if you put J equals 1, F0 minus 2B, which is smaller than F0 because we are subtracting. Still smaller energies, minus 4B, minus 6B, as we may continue on this side. Let us now look at which transitions is this. The first one. Initial J is 1. Final J must be, we are talking about J to J minus 1. If initial J is 1, what is J minus 1? 0. So this is 1 to 0, initial, final J. It is this, 1 J to 0. All right? This one, 2 to 1. This one, 3 to 2. All right. This graph and the formulas over there indicate the frequencies of all the photons that could be absorbed by the sample. When you frequency scan the sample, you have a light source. It's capable of changing the frequency it generates, and then at exactly these values, F0 plus 2B, or F0 plus 4B, or F0 plus 6B, photons with such energies will be absorbed. Similarly, F0 minus 2B, F0 minus 4B, and so on, those photons are also going to be absorbed. Next, let us look at the intensities. Now, intensities of absorption are proportional to the initial populations of the levels. Initial. For example, if at an initial level there are no molecules, then there can be no absorption, because by definition, if there is nothing, could there be any absorption? No, there must be something there in order to absorb photon. So, initial populations are just the rotational distribution, because vibrationally all the molecules are in the lowest vibration level. There is no vibrational distribution. All the molecules, 100% of the molecules are in the lowest vibration level. But there is a rotational distribution which belongs to the ground, lowest vibrational level. That distribution we had discussed in our pure rotational transitions. So, for example, this is intensity. The height here is proportional to the population of the J equals 0 level. Initial level is J equals 0. The height of this transition is proportional to, what is the initial J value? 1. It's proportional to the population of the J equals 1 level of the ground level. So, and in our calculation, this was larger than the J equals 0 population. Then this one was even larger. This height is proportional to population of J equals 2. This is the initial. I'm not going to draw the remaining, but you may see it from the notes. Let us come to this side. Population of this level is also proportional to initial level, but what is the initial J number? J is initial J 1. Here it was also 1. So the height of this absorption, the intensity of this absorption is exactly the same as intensity of that absorption. This height is the same as, should be the same as this height, because initial populations are the same. J equals 1, J equals 1 here also. When we come to here, for this absorption, this time J is equal to, J is 2. But here in the R branch, there is also J equals 2. So the height of this transition must be same as this one. The height here is the same as that one, because in both cases initial level is J equals 2. Here J equals 2, here also J equals 2. Okay, so we can display the intensities and also photon frequencies which are absorbed on the P branch, complete the picture, and also on this side. And this gives out the final picture. Please note that F0 is the spacing between vibration levels. All right. Do we have any absorption at a photon frequency which is exactly the same as F0? No, that transition is not allowed. Once again, you must remember that in this picture, we are talking about transitions in which the vibrational state has changed. Initial vibrational state is the ground vibrational level, V equals 0. The final vibrational level is V equals 1 in all of these transitions. So delta V is plus 1. But at the same time, there is delta J selection rule. Delta J is plus 1 for the R branch. For the P branch, delta J is minus 1. Let us look at energy difference or frequency difference between successive absorptions. 4B minus 2B is, what is it? 2B, isn't it? This is 2B. What about 6B minus 4B? It is also 2B. And you may imagine that for the remaining absorptions, the difference between successive, the one and its neighbor, is a constant. It is 2B. On this side, what is the spacing? For instance, this spacing, minus 2B minus 4B, again, 2B, and also goes. So, if you consider from left to right, in the R branch, or in the P branch, the line spacing, the term is line spacing means difference between this level, this absorption, this photon frequency minus that photon frequency, or that one minus that one, successive. But notice that the line spacing is 2B until here, to this point. Then this is plus 2B gives F0, but F0 is not allowed. So line spacing at the center is this value minus that value. What is it? 4B. So in the experiment, of absorption. We have machines which can detect the absorption frequencies and then give us a graph. The graph is similar to this one, but experimentally obtained. Then, when you examine, you look at the differences between line spacing, and it turns out that the experimental picture graph fits what we have been discussing here. Line spacing is nearly constant, so that you say it is equal to 2b. The actual value is obtained from experimental data. So you write 2b is some number which obtained from experiment. Because this number is known, you can obtain value of b. b is equal to this value divided by 2. This number is obtained experimentally. So this way, experimental determination of rotational constant is obtained. Also, in the same picture, in the middle somewhere, you will see a gap. Instead of 2b, the spacing will be 4b. This gives you the signal that the center of it is the vibrational constant, which is f0. All right, take a break.